Okay, so this is a set of notes now on inverse matrices. All right, so this is kind of like how do we get to division in matrix arithmetic? Okay, so if I have an inverse matrix, I'm going to let myself have a matrix A, which is going to be n by n. So this has to be a square matrix, okay? In order for a matrix to be invertible, it has to be square. And then I'm going to have another matrix called A inverse, also a square matrix. And if I take A times A inverse, I get something that's equal to A inverse times A, and both of these is equal to the n by n identity. If that's the case, then we say A inverse is the inverse of A. So we'll call A invertible, and we will call it non-singular. Okay, not all matrices are invertible. Like a prime example, this matrix is not invertible because no matter what you multiply it by, you're going to get 0 and you're not going to get an identity. So that thing is not invertible. There's a lot of non-invertible matrices, but there are a lot that are. And that's going to be a big question in this course, is like, how do I know if a matrix has an inverse? And it's not hard to figure out, but we'll get there. Okay, right off the bat, we get this idea that the inverse for a matrix has to be unique. So we get a theorem that says if A is an n by n matrix invertible, then A inverse is unique. Okay, it'd be nice to know that you can't take two different matrices and multiply them by A and get the identity. Now, proving this is actually quite simple. So what you do is you suppose not. Suppose B and C are both inverses of A. Well, watch what happens. So if I take A times B, I have to get the identity. Okay? So this means that C times AB has to equal C times I, which has to equal C. All right, well, I can associate C times A times B has to equal C, but C times A has to be the identity if C is an inverse, which means that B equals C, and I'm done. So if B and C are both inverses, they got to be equal. They have to be the same matrix. So that means that any inverse must be unique. All right, one of the nice things about matrix arithmetic is it starts to make proofs easier because you don't have to actually know the structure of the matrix to prove things about it. And that's what we just demonstrated here. All right, so we're going to get a couple quick properties about inverse matrices. One, this seems pretty trivial, but if you take the inverse of an inverse, you get back the matrix. That's not all that off the wall. If I take A times itself K times and invert it, that's the same as A inverse times itself K times. You can stop and do that. That's an inductive kind of argument. If I have a scalar times a matrix and I invert it, then it's 1 over the scalar times the inverse of the matrix. Because it's like, aha, C to the negative 1 is 1 over C, right? That's why that works. Okay, there's an obvious thing that has to be said here. C can't equal 0. Okay, number 4. A transpose inverse is the same as A inverse transpose. That's kind of nice. And number 5, just like the transpose, if I take the inverse of a product, you have to change their direction. That's going to be B inverse times A inverse. And remember, they're not commutative, so that's not the same as A inverse times B inverse. We also get some cancellation properties. Okay, so this is where this starts to feel like division. So if A times C is equal to B times C, then this implies that A is equal to B. Why? Because I can multiply both of these on the right by C inverse, which would give me this. And number 2, if I have C times A is equal to C times B, I can also do left-hand cancellation, which will get me back to A equals B. This only works if C is invertible, however, right? No inverse, this doesn't play out. All right, so there's your cancellation properties. Okay, so I know we've used Gauss-Jordan to solve systems of equations, and this may seem like overkill, but there is a purpose to this. So let's give you a system. 2x1 plus 3x2 plus x3 is equal to -1. 3x1 plus 3x2 plus x3 is equal to 1. 2x1 plus 4x2 plus x3 is equal to -2. All right, in the last set of notes, we wrote this as a matrix equation. We write this as 2, 3, 1, 3, 3, 1, 2, 4, 1 times x1, x2, x3 is equal to 1, 1, or sorry, -1, 1, -2. Now, why do we do this? Because this is like my ax equals b. And if a is invertible, which in this case it is, I can say that a inverse happens to equal -1, 1, 0, -1, 0, 1, 6, -2, -3, happens to be that. If I take that inverse and multiply it by b, right? Because if ax is equal to b, then x should equal a inverse b, right? Because I take a inverse of both sides here. These guys cancel out, leaves me with x. A inverse is b. So if I take a inverse and I multiply that by b, this will give me x, which happens, if you work out that multiplication, happens to be 2, 3, -14. And you're like, but I could have just done Gauss-Jordan. This is like way too complicated and I don't need to do this. But here's why. Here's why we do this, okay? Is that once I have this inverse, I can like go ahead and now just change these values up here. All right, so instead of -1, 1, and -2, I can make these guys like 4, 8, and 5. And then I ask, okay, now solve this system. Look how short I would have like punch it all in again, have it all recalculate. But no, I already have A inverse. A inverse is this guy, right? A inverse times B is still going to give me X. So I just substitute out these guys, put in 4, 8, 5, and now I get the new values, which is going to give me 4, 1, -7. So once I have the inverse, I don't have to keep resolving the equation every time I change the constants. And this is actually turns out to be pretty useful in the real world, because what would happen here is this is like the world in which my problem is living, and it's being described by these linear combinations. This is my desired result. These are my outputs. So the question that I'm asking when I'm solving a system of equation is, in order to get these outputs given this world, what do my inputs have to be? So if I can find the inverse of the world and multiply that by my outputs, it will return my inputs. Aha! So this is actually like a pretty useful idea if you're solving real world problems where the world stays fixed and the desired outputs are changing and the inputs are needing to be dealt with. Okay, so we're cheating a little bit here because like if you look back in the video there, like the inverse itself just seems to like come out of nowhere. Like, how'd you get that inverse and where did it come from? Okay, so there's kind of a game here a little bit. There's an easy way to do this for 2 by 2 matrices by hand. Okay, so if I have a matrix in the form A, B, C, D, and I want to calculate its inverse, there's a bit of a trick to this. I take 1 over AD minus BC, so that's this way minus that way. Okay, times, and then I switch the A and the D, and I make the B and the C negative, and you will get an inverse for a 2 by 2 matrix that way if it exists. Okay, note something's going on here, right? If AD minus BC is equal to 0, no inverse exists. Okay, so that's just a little hint there. There's a way to figure this out. So this is pretty simple for 2 by 2s. Usually for 3 by 3 or bigger, what we tend to do is we actually use Gauss-Jordan. Okay. So the following is true. If I have an augmented matrix, right, A on the left, and I have the n by n identity on the right, and I use Gauss-Jordan on that, what it returns is the identity on the left, and lo and behold, a inverse on the right. Now that may take some convincing to work with here, but like if I took my A matrix, right, which was 2, 3, 3, 1, 3, 3, 1, 2, 4, 1. That was the A matrix for my system of equations above here. And then I put next to that the 3 by 3 system of equations, and I do RREF on this, or the 3 by 3 identity here. I'm going to get the 3 by 3 identity on the left, and lo and behold, it will give me negative 1, 1, 0, negative 1, 0, 1, 6, negative 2, negative 3 on the right, which is what I identified in the problem as a inverse. So you can actually use, Gauss-Jordan to get you to an inverse matrix if it exists. Oh, sorry, this should not be 0, 0, 0. This should be 0, 0, 1. There we go. All right, because note, if I don't get the identity on the left, then I don't have an invertible matrix. Okay, so try toying around with all of this, seeing what you can do, and we'll start making some use of it next class. Thank you.